Hello everybody and welcome to this week's video in which we will be deriving the momentum operator. It is in a number of QM textbooks. You kind of just get told that we have this p hat, which is minus I h bar times the position derivative. This seems a bit arbitrary. I mean, obviously you're somewhat aware that in classical mechanics we have a momentum, which is mass times velocity, which is then mass times the spatial derivative, the dx dt, which is the temporal derivative of space. So, okay, well, suddenly there's no mass, there's an imaginary unit, there's this thing, and then there's the space derivative, not a time derivative. Well, this doesn't. What's going on? I'm scared, and also a little QM student who doesn't know anything. Well, it's basically. I mean, you can derive it, and that's what we're gonna do. I mean, space is homogeneous, right? And so, if we want to have a homogeneous space, we need a unitary operator that can move our quantum states around space. So we'll do that. We're gonna look at we'll actually start off by putting a line under here. I'm forgetting all about momentum for a minute. What we're gonna do is we're gonna define a space translation operator. It's gonna be t hat, and it takes in an input epsilon. That's not That's an epsilon, yes. And it will take a state vector. I can't draw them like that anymore, can I? Like that. And then it will shift it by a distance epsilon. So we can look at the position basis. So, well, this 5x represents, this is going to be bra x ket phi, and this represents the probability of finding r particle x. And well, if we translate it to the right, what do we get? Well, we'll start off by evaluating it at x minus e, because that's going to be a translation to the right in our 1D space or whatever. So we'll say t hat epsilon phi x, psi of x, sorry, is equal to psi of x minus epsilon. Cool. Now, in this case, epsilon is really infinitesimally small. So we can expand the right-hand side of this to be a Taylor series. So this is going to end up being psi of x minus epsilon d psi of x dx plus epsilon squared over 2 second derivative of psi of x dx squared plus dot dot dot. And then we can of course pull out a psi of x, and this is then, sorry, times 1 plus epsilon d dx plus epsilon squared over 2 factorial, sorry, that's be 2 factorial, d squared dx squared. I went to see a concert this evening at the Royal Albert Hall, and it was wonderful, but it means I am dilapidated, and hence I'm sorry if I make a simple mistake. It will be rectified in general. Well, what do we have here? This is the exponential operator. This is actually exp of minus x, being, so exp of minus x, that being the sum of minus x to the n over n factorial. Which I realise I don't represent very well there because there's no negative sign, so that should be a negative, and our oscillating terms show that it must be minus n, and so we now know that our translation function is some exponent of minus epsilon dx dt. Sorry, ddx, not dx dt. Well, how do we know this? Because obviously our things here in our Taylor series that are being squared as this, or at least if you were to compare these two, what is being, well, the 0th one is just going to be 1, obviously, and this is epsilon ddx to the 1 over 1 factorial, which is 1, and then over 2 factorial, etc, etc, etc. Okay, so at the very least now, we've managed to see how we can get something out of this translator operator. I think it becomes fairly clear now what we're starting to get at. So then this is roughly equal to I minus epsilon dx plus our error terms. That's fine. I being our unit. But remember from our video 2 weeks from my video 2 weeks ago on operator algebra, we want to consider this quantum mechanically now. So what we'll do is we'll look at a normalized state. We'll have a state psi, which can be normalized as bra psi, ket psi, being equal to 1. And this is normalized. And then we can also have a translated state, which is ket of psi prime, psi dash rather, and then this is our translated, our operator of translation acting on psi. And that also needs to be normalized, so, well, we can work through that, and we require that this is equal to 1. So let's expand. Well, what do we have for each of these? We have psi. Then, of course, because this is a bra rather than a ket, this is going to be the transpose, or the Hujma Flippy of it, the word has escaped me for the cross. You should all know what that means by now. I've definitely used it enough times though. And well, we now know that the translation operator from this, what do we have here? Well, this is 1, and that's equal to 1. So 1 times something is equal to 1. So T transpose epsilon, or like the opposite of, times T epsilon is equal to 1. And, well, any unitary operator, as we've gone over, can be parameterized by a Hermitian generator, which we can call k hat. So then we have that T epsilon must be equal to I minus I epsilon k hat. I here being the unit, and identity rather, and I here being the imaginary unit. This is to guarantee that k is Hermitian. I feel like I'm saying that wrong. Hermitian, Hermitian. Oh, it doesn't matter. Say it in my head. Well, the last thing we need is units. Funnily enough, of kilograms, meters per second. Well, how do we do that? First of all, we can look at Noether's theorem, which I haven't covered yet. I'll do that at some point. It's a bit of a head scratcher, I think, to explain the video, but I'll try my best. Anyway, by Noether's theorem, you can go and look it up. We have the generator of the spatial translation is conserved because space is homogeneous when space is homogeneous. So in classical mechanics, this is just momentum. And that's why we need to match units. So how are we going to match units? Well, we need a factor of h bar, which has units of joule seconds. So we can then take units here, and k hat is equal to our momentum operator over h. I guess it's h or h bar, doesn't really matter. Okay, so we can throw this back into there, and now we have that t of epsilon is equal to I minus I over h bar epsilon p plus O epsilon squared. Cool. Well, now we've got a few bits. We've got actually 2 bits. And we also have that t hat epsilon is equal to I minus epsilon d dx. And we can ignore that for the time being. I can put this here. So that it is to be shown that they can be ignored because they cancel. So this is our geom, and this is our qm. And these are our 2 translations. So this one comes from the Taylor series that we did, and this one comes from our generator function. Well, what do we do when we have 2 expressions of the same thing? Equate them. So we will have that I minus I over h bar p hat. I'm gonna ignore those because they would literally just cancel out on each side. By that logic, I would also ignore those because they cancel out on each side, and those because they cancel out on each side. So we have that I over h bar epsilon p hat is equal to epsilon d dx. Well, this is starting to take more shape. Let's throw some things to some sides. In fact, we can now get rid of this on each side, and we have that I over h bar p hat is equal to d dx, and we can multiply both sides now. Now a trick actually is, instead of to divide and subtract or whatever, if we multiply both sides by I minus I h bar, we can clear some things up. So we get rid of the h bar from that side. In fact, I may as well write it out because it's actually quite a neat little trick. Well, what's happening here? Those are cancelling, obviously, and then, well, I times I is minus 1 times minus 1. That's going to cancel, and we are left simply with the very fact that p hat is equal to minus I h bar d dx. Well, neat little formula, isn't it? Let me put it in a proper box. There we go, lovely, lovely box. Whilst I'm transfiguring this, let's talk about a few things. Well, we've seen where we've got our P from, that is from Noether's theorem. Up here, from our quantum mechanical perspective, well, we need to be able to, I mean, it comes from our algebra of operators. And then from that we can establish that Noether's theorem says that we have to have a momentum operator, classical momentum operator, and then further up we have a geometrical idea, which is, well, if you want a function that moves something in space, then this is a way of generalizing it, and it just so happens that ends up being exponential. So we gain the spatial derivative from our geometry, we gain the terms of I and h bar and the minus sign from something else, which is the quantum mechanical side. So the I is from the necessity of itself in the generation function, so that it's a Hermitian operator. And then the H bar is to work with units. There's one more thing I would like to cover in this video, which is, given this, it should then be true further that the commutation relation of x and p, which can be written like this. I'm now going to drop hats because we are doing operator algebra. I h bar. That is what this is telling us. And we can get this without doing any derivative nonsense. It's actually fairly easy. Well, let's start again. So let's do x. I'm going to add hats here. T epsilon times our psi of x. Well, judging based on what we did before, we know that this is then T epsilon psi of x minus T hat epsilon x hat psi of x, nice and simple. And we can compute each term here, so we'll do 1 and then 2. 1, what do we have? Well, this is gonna be x hat. Well, we know what that is. That's merely psi of x minus epsilon, which is x psi x minus epsilon. And then the second term is possibly even easier, because we have the same thing, except it's negative, but x times it, so it will be x minus epsilon psi of x minus epsilon. That's not epsilon, that's an e. Well, now we subtract them, so we have that not h, x t epsilon psi of x is equal to x psi x minus epsilon minus x minus epsilon psi x minus epsilon. Well, that's a lot of things, and this is going to leave us with x minus epsilon of that, which is obviously just going to be epsilon. And then, well, we can expand this, and it is as simple as this being epsilon, 5x plus some error terms. Now this holds for any arbitrary phi, so we can get rid of that and call it an identity, and so we end up with x hat t hat of epsilon being equal to epsilon I. Useful that is, because, well, we have an expression for this in terms of p, and so we can plug things in. Let's actually, so x hat I minus I over h bar epsilon times our momentum is equal to epsilon I x hat I. Well, that's an easy one to compute, because that's 0. So that cancels, minus I over h bar epsilon xp. This is epsilon I as well. And so minus I over h bar, I think you can see where this is going, xp is equal to epsilon I, and so epsilons are going to cancel, and we will use the same trickery that we used last time, but now we have a minus sign on both sides, so it will actually end up being that x hat p hat is equal to I h bar I, and of course we know that in our regular space, x hat p hat is equal to I h bar. Here is another fairly beneficial conclusion. So yeah, we've come to a couple of useful conclusions here. We've come to the conclusion that these two commute to give IH bar, which kind of again gives another reason why that might show up in our momentum calculation. I'm going to copy and paste this down to the bottom as well so that it makes for a great thumbnail. Because you know I put so much effort into my thumbnails. They're truly beautiful and things. But yeah, I hope you have enjoyed this video. It was a slightly shorter one, with some slightly more basic stuff going on, I think, but no harm in it. Lay a basis for understanding some of my other videos, which might be significantly more confusing. So yeah, and I guess if you are a early quantum mechanics student and have picked up a textbook and gone, help, I hope this has caused some gentle reassurance that this isn't actually that bad. Anyway, have a nice week and I will see you soon. Goodbye.